This section is about continuity, and we will begin with a very realistic example by looking at the graph of a function that is very definitely not continuous. In 2009, Congress passed legislation to raise the federal minimum wage for the first time in 3 years. The graph actually here shows how the federal minimum wage has varied since it was first instituted in 1938. So in 1938, it was way down here at the bottom. And was a lot less than $1. In fact, I can remember in 1938, my grandfather actually worked at a creamery, and in addition to all the dairy products that he could take home, his actual wages were a grand total of about 25 cents a day, if you can imagine. Now, the minimum wage has increased quite a bit since then. When I entered the workforce in 1970, the minimum wage was $1.25. And it increased, as you can see, over the years until around 1988, it had reached the point of being about $3.75. Now, the idea here isn't just to talk about minimum wage, because as you know right now, minimum wage is about $7.25, which is this part of the graph up here. But the part that we want to look at more closely is the idea of where it is continuous and where it is not continuous. So notice here that in 1997, that's the year we're going to pay the most attention to right now, in 1997, which is right along about here, as you approach from the left, f of t is equal to about 475. See, I think I probably did not hit 1997 very well, so let me back up and try that again. So 1997 is along about here. Notice that if you approach 1997 from the left, that f of t is $4.75. But if you approach it from the right, it's $5.15. So here's the $4.75 from the left. But if you approach from the right, it's $5.15. So based upon the fact that if you are trying to trace this function, you can see that it has many discontinuities. And that's going to be everywhere that you see a sharp break in the function, like from here to here, or from here to here, or from here to here, or from here to here. In fact, every year when the minimum wage actually changed, you have a discontinuity. So where those breaks are is where we say that the function is discontinuous. And you kind of have an instinctive idea of what discontinuity means, because you know that when you have a graph that is not continuous, it means that you had to pick up your pencil and move it off of the graph and then put it back down again in order to be able to continue tracing on the function. So if we use a function to model the behavior of the federal minimum wage over time, what we see is that it has a lot of discontinuities, and that's because every time the minimum wage was increased, there was a sharp break in the function. Finding limits would be difficult using algebraic methods in situations like that, and limits can't be found at any of these breaks in the function because the right-hand limit doesn't match the left-hand limit. So this is the mathematical definition for continuity. Actually, this is actually a test for continuity. And basically what we say then is that a function is continuous at x equals c if, first of all, f of that number, whatever c is, if f of c is actually defined. And that the limit as x approaches c exists, and then lastly that the limit as x approaches c for the function is actually equal to f of c. And if all three of those steps are not met, then the function is discontinuous at c. So let's look at some examples. Let's determine if the function that's graphed at the right is continuous at x equals 3. Now, instinctively, I hope you would realize that actually the answer to this question is going to be no, it's not. And it's not because if you look at that value right there, you know that the function itself is not defined at x equals 3. There is a hole in the function at x equals 3. So step 1, does f of 3 exist? And our answer, as we can see, is no. Therefore, it fails at step 1. We can't check off even step 1, so we go ahead and go to the conclusion that f of x is not continuous. But we have to be specific. It is not continuous at x equals 3. It would be continuous, on the other hand, if we ask, is the function continuous at x equals 0? Because at x equals 0, f of 0 is 2. And if you approach 0 from the left, you approach the value 2. And if you approach 0 from the right, you approach the value 2. And the function is defined as 2 at x equals 0. So all three of the steps would be met for other values. In fact, any other values on this function except where that hole is at 3. So the second problem we have says determine if the function graphed at the right is continuous at x equals 0. So we're looking to see what's happening when x is equal to 0. And again, step 1 says, is f of 0 defined? Does f of 0 exist? Those both actually mean the same thing. And we see, actually, then, that, yes, f of 0 does exist. F of 0 is equal to negative 1. So, step 1 is a check. Yes, f of 0 does exist. But then in step 2, we say, does f of 0, or does the limit exist? Is the limit as x approaches 0 from the left equal to the limit as x approaches 0 from the right? Well, we see that the limit as x approaches 0 from the left is -1. But then we also see that the limit as x approaches 0 from the right is +1. So is the limit from the left equal to the limit from the right? And we know that -1 does not equal +1, so no. Therefore, the function is not continuous at x equals 0. But it's very specifically at x equals 0 that there's an issue, because we have this break. If we were talking about any value that is greater than 0, it appears to be continuous, because we don't lift our pencil on that side. For any value that's less than 0, we don't have to lift our pencil. The limit exists, so it's continuous everywhere it appears. And I said f of x throughout all of this. It's actually h of x. Hopefully you'll forgive me for that. So h is continuous everywhere except at x equals 0. So here we have another example of continuity. And again, we're going to approach it step 1, step 2. So step 1 is f of 4 defined. Or does it exist? I'm sorry, that's G. Is G of 4 defined? Does G of 4 exist? So to determine that, we come over here and we look to see where 4 is. And we notice that while it's not on that line, f of 4 is defined. And it has the value of 1. So we know that G of 4 equals 1. Does it exist? Yes. So it passed step 1. But now we need to evaluate the limit as x approaches 4 from the left of G of x, and the limit as x approaches 4 from the right for G of x. And we see that if we approach 4 from the left, that we seem to be approaching the value -2. But if we approach from the right, we see that we're also still approaching -2. And since the limit from the left is equal to the limit as x approaches 4 from the right, since those two are in fact equal, then it passes step 2. So then we move on to the next step, third step, and that's the important one in this case. Because the third step says, okay, if it passed step 1 and step 2, is the limit as x approaches 4, which, if you recall, that limit does exist, and that limit is -2, because you approach from the right and the left, and you're going to approach the function value -2. But is that limit equal to f of 4? And we remember then that f of 4 was not 2, it was 1. And since 2 does not equal 1, then the answer is no. G of x is discontinuous at x equals 4. Here we have a function that we have the graph of it, and it says, is this one continuous at x equals -2? So we want to investigate what's going on at -2. But notice that at x equals -2, we have an asymptote. So, does f of -2 exist? Well, we see that what happens is that our line clearly approaches -2, but it never actually reaches it, which is why it's always climbing ever closer. So the answer to this question then is no. F of x is discontinuous at x equals -2. So here's the definition of infinity on a closed interval, and it really is it's making a lot of fuss about really what is not something that's that terribly important to us. Basically, if this function is continuous on the open interval, and what the open interval means is if you leave out its endpoints. We're not talking about at x equals -1 or at x equals +1. Is it continuous on the open interval? Yes, from -1 to +1. This function is continuous because you can trace along it from -1 until you get to +1 and never have to lift your pencil off the graph. The limit exists at every value between -1 and +1. it's continuous from the right at x equals a then, whatever that number is. A is any number between the beginning point and the ending point. And it's continuous from the left at x equals b. So all we're saying is there's no difference in continuity for a closed interval and an open interval. You don't have to talk about continuity at the end points of the interval. That's really the gist of what that's saying, root points. So we're going to review some functions here and talk about where these functions are continuous. This particular function is a polynomial function. I'm going to give you some examples of polynomial functions just to remind you. Polynomial functions look like, oops, let's get a better color than that. Look like f of x is equal to x squared, or f of x equals x cubed minus x squared plus 2x minus 1. Can have lots of terms. It could look like f of x equals x to the 4th minus 5. So a polynomial function is also what we call a power function. And you may remember from Math 1630 that the power function refers to the fact that the x variable has powers on it other than 1. And those powers will tell you how many times that function turns. Like, for example, the quadratic function turns once. That's what f of x equals x squared looks like. This function, I'm pretty sure it's not this graph, but this function would have the same shape as that graph because it's a cubic function, which means it turns twice. Once here and once here. So we're pretty sure that's a cubic function. And then x to the 4th power can actually look like a quadratic graph, or it can look like 1, 2, 3, 4 turns. But the key here to think about is that in a polynomial function, we're not violating either of the cardinal rules in math. There are two things that we are never, ever, ever allowed to do in math. Division by 0 is undefined. And square root or any other even root of negative values is also undefined. So you can't do this and you can't do that. But since we're raising it to whole powers, we're not taking square roots or cube roots or anything else. And we're not trying to divide any of these terms by the variable, then a polynomial function then doesn't have any restrictions on its domain, and therefore it is continuous everywhere. So if you have a polynomial function, it is continuous everywhere, or for all x. Function that we're going to look at. In this function, we're going to look at a rational function, a function where you have a fraction. And if you have a fraction, you know that by definition, in a fraction, you have a numerator and you have a denominator. And if your variable is in the denominator, then whatever that denominator is, whatever that variable value is for x that causes the denominator to be equal to 0 would cause division by 0. So, for example, in the one that we're looking at here, this rational function has an asymptote at some value that's negative. It also has a horizontal asymptote. I'm not telling you that it only has one asymptote, but at this point we're not terribly concerned when we're talking about continuity. We're not so concerned about its horizontal asymptote. We're interested in the fact that it has a vertical asymptote, which tells you at whatever this value is, whatever value A is, then that function is undefined at that value A. So this is the part you worry about dividing by 0. So if you have a value of your variable that would make you divide by 0, you know that that's a violation of all the rules of math, and therefore it is continuous for all x where the denominator of the fraction can't be 0. The next kind of function we're going to look at is a root function or a radical function. And in this radical function, what cannot happen is you cannot take an even root, like a square root or a fourth root or a sixth root. Square root's the most common. You cannot take the square root of a negative number. That, again, is not allowed. So this function is only going to be continuous on some interval where its radicand, which is called ax plus b, is equal to or greater than 0. And we'll look at a more specific example of this in a minute. This is an exponential function. The exponential function you may have seen before would be a function like y equals e to the x, or f of x equals some number, which we'll call b raised to the x power. Now, the truth of the matter is, exponential functions, x can be anything. It can be positive, it can be negative. X can actually be 0. For example, if you have 2 to the x power, then 2 to the negative 2 is equal to 1 over 2 squared, which is 1 over 4. And if you have 2 to the positive 2 power, that's equal to 4. And since we've talked about an example of the negative, and we've talked about an example of the positive, what would it mean if 2 was raised to the 0 power? Well, 2 raised to the 0 power is 1, so it still has a definition. So for that reason, exponential functions are continuous for all values of x, positive, negative, and 0. Now the logarithmic function, remember the exponential, and this was an exponential growth function, by the way. The exponential function look like that. Notice that your logarithmic function, on the other hand, comes up from the bottom and increases without bound as x gets bigger. So since it comes up from the bottom, and you notice that there's nothing over here, because that function just keeps approaching negative infinity on that side, and it approaches positive infinity on the other side. So what this one has as a restriction is that x cannot be negative. It can be 0. It is possible for x to be, I'm sorry, it is not possible even for it to be 0. I just about misspoke there. So our restriction here, if you have a logarithmic function like f of x equals the natural log of x, or g of x is equal to the base 10 log of x, either one of those, x can only be positive. So the restriction is it is continuous for all x values that are greater than 0. X can't be 0 and it can't be negative. So here we've got a radical function, and we're going to find all the values where this function would be discontinuous. So what we know from algebra and from finite is that a square root function is only defined if 5x plus 3 is equal to or greater than 0. And that's because we can take the square root of 0, but we can't take the square root of negative numbers. So if 5x plus 3 has to be equal to or greater than 0, that means 5x has to be equal to or greater than negative 3. Because we subtract 3 from both sides. And then that also means then that x has to be equal to or greater than negative 3/5. Now to see why that's so, suppose x is equal to, let's see, something bigger than negative 3/5, like, oh, I don't know, negative 1/5. Well, 5 times negative 1/5 plus 3, 5 times negative 1/5 is negative 5/5 plus 3, which is negative 1 plus 3, which is 2. And can you take the square root of 2? Yes. Does it come out pretty? No, it doesn't have to come out pretty, but you can take the square root of 2. But let's suppose we pick a number on the other side of negative 3/5. Like, for example, negative 2. Let's let x be negative 2. If x is negative 2, then 5 times negative 2 plus 3 is negative 10 plus 3, which is negative 7. Can you take the square root of negative 7? Try it on your calculator, and your calculator will say error, non-real result. So this is not real. So for that reason, that function is not defined for any value where x is less than negative 3/5. So the function is discontinuous for all x less than negative 3/5. So since it asked us where it was discontinuous, we say where it isn't continuous. It is continuous, on the other hand, when 5x plus 3 is equal to or greater than 0, and it is continuous on the interval from negative 3/5 to infinity. Just a quick reminder of how you write that notation. So that interval is negative 3/5 to infinity. And this one actually includes the negative 3/5, so the proper symbol there would have been a bracket. So this is where it is continuous. Now here we have a rational function because it's a fraction. And remembering that this is a fraction, it has a numerator and it has a denominator. And we're not terribly worried about that numerator, but we are worried about what happens in the denominator because we know that the denominator is not supposed to be 0. So that means that 2x minus 7 equals 0 would cause us a problem. So that's going to be where it's discontinuous. So if 2x minus 7 is equal to 0, that means 2x is equal to positive 7, and then x is equal to 7 halves, or 3.5, or 3.5. And here, if you're in my math lab, you'll have to pay attention to how they say they want that answer. But as far as I'm concerned, 3.5 is a perfectly good answer. So f of x is discontinuous. At x equals 3.5. Because that would cause division by 0. Here we have a function, e raised to a power with a variable. This is an exponential function. Okay? Exponential functions are continuous everywhere. So basically what it says is that you can put in anything you want to for that x. A positive number, a negative number, a 0, makes no difference. E raised to any power, if e is raised to some positive power, it's going to be defined. For example, if that value of x was 4, that would give you e to the 5th power. And e to the 5th power is a number. You can check that on your calculator. If that number had been negative 10, that'd be negative 20 minus 3, which is negative 23. And e to the negative 23 power is a legal value, because e is a number and negative 23 just simply is a large negative exponent. So it's going to be a small number, but it is defined. And even if x was equal to 0, then that means that e is to the negative 3 power, because 2 times 0 minus 3 would be negative 3, and e to the negative 3 is defined, no problem. And even if 2x minus 3 were equal to 0, which would happen if x was 1.5, still, e to the 0 power, just like everything else to the 0 power, is equal to 1, so it's still defined. So all values of x where f of x is e raised to the 2x minus 3 is discontinuous, well, f of x, this particular f of x, is never discontinuous. Now, this is a great place to talk about discontinuities, because this is what's called a piecewise function. The piecewise function follows a linear expression as long as x is negative. It also follows a linear expression when x is greater than 3. But any place that's greater than 0 but less than 3 or equal to 3, it follows a quadratic function. So basically, this is going to be a line that slants up rather steeply. And then when x is equal to 0, it's going to be x squared. But then when you get to 3, and notice that the cubic actually contains the endpoints because there's where your equals to are, then it's going to have another part that goes up because both of those are positive slopes. So the place where there's likely to be an issue is going to be either here or here when it switches rules. So what we're going to do is first we're going to check what goes on with the function at x equals 0. So we're going to look at it. What is the limit, or the value of the function actually? What is the limit as x approaches 0 from the left, which means it's going to be following that rule. Well, 5 times 0 is 0, and 0 minus 4 is negative 4. And f of 0 is 0 squared, which is just 0. So what that tells me, since the function is defined to be 0 and the left-hand limit is defined to be negative 4, and negative 4 is not the same as 0, then we got a problem. And that means the function is discontinuous at x equals 0. So then the other one we'll have to investigate is going to be what's going to happen around 3. So if x is equal to 3, f of 3 is equal to 3 squared, which is 9. But then if it's more than 3, if x is greater than 3, then it's x plus 6. And 3 plus 6 is also 9. So that means that it is continuous because these two are equal. It is continuous at x equals 3 because these two rules give the same answer at x equals 3. But again, at x equals 0, these two gave different answers. And if you look at a graph, here's a graph that's very similar to what we were just looking at. So the point of discontinuity here, you can see. Whereas at x equals 1, even though the limit comes up toward 2, this rule also goes to 2. So this one is continuous at x equals 1. But it is discontinuous at x equals 3. Now this is not the graph of the previous function, keep that in mind. It's just another example. This is a different graph. So from the graph, it's easy to find your discontinuities. If you have to work strictly from the equation, then sometimes it's a little more trouble. Now, notice here the graphing calculators actually have the ability to draw piecewise functions. So in your graphing calculator, you can actually enter in all the rules for an equation on one single form. You don't necessarily need to enter this at y1 and this at y2 and then this at y3. You enter all of that in at y1. And what you do is this function would actually look like this. This would be for the function f of x is equal to x plus 1 when x is less than 1, x squared minus 3x plus 4 when, and here you have to make notice of the fact that in your calculator you have to break that part up, because this is actually saying when x is between 1 and 3. And then the rule for x greater than 3 is 5x minus 1. I'm sorry, 5 minus x. So there's the piecewise function that's graphed here, and this is how you would enter it into the calculator. So I would suggest that you try that out and see if you don't get a graph that looks like this one. So example 4 is a realistic example. Says a trailer rental firm charges a flat fee of $8 to rent a hitch. That's kind of like fixed costs. You pay them $8 to rent the hitch, even if you don't ever put it on the car or use it. The trailer itself is rented for $22 a day or part of a day. So we want to let X represent the cost of renting a hitch and a trailer for X days. So here's what happens. You walk in and at 0 days, this is the day you actually come in. Day 0 is your day that you walk in. Your cost, C of X, is going to be $8 regardless. So let's say that all you did was rent the trailer. I'm sorry, rent the hitch and the trailer. But you never left with it. You didn't keep it. You changed your mind. You brought it back. So at day 0, you're going to pay $8. If you rent it, if you do anything at all, it's going to cost you $8. Now, if you rent it for the whole day, one whole day, then that's going to cost you $8 plus $22 for that day, which would be $30. So at day 0, it's going to cost you $8. But at the end of the first day, as long as you bring it back at the end of that first day, it's going to cost you $30. And then immediately, what you're going to see happen is that if you keep it for the second day, you're going to add another $22, which is going to be $52. So when X is equal to anything more than 1, but up to 2. From 1 to 2, it's going to cost $52. So once you've rented your hitch, this is your actual cost on the first day. And that would be an open circle. On your second day, you jump up $22 more to $52. And that would also be another open circle. So all of that day by the end of the day, all of that is going to be $52. Now then, if you add another day to it, that adds another 22 to our 52, which is going to be 74. So at the beginning of the end of the second day and all the way into the third day, it'll be $74. And then the next day it's going to go up $22 more, so that'll be $96. And then at the beginning of the fifth day, it'll still be at $96, but you know, if you bring it in a half hour after they open, then your cost is going to jump up to $108. And so on. So this is what the graph would look like. And there's a much better picture of that graph. Now, all the values A for which C of x is discontinuous. Well, the limit as x approaches 1 from the left is $30. But the limit as x approaches 1 from the right is $42. And the same thing at x equals 2, and x equals 3, and x equals 4, and x equals 5. Here's your discontinuities. And they're all discontinuous for the same reason. Your right and left-hand limits don't match. The function is defined, but the right and left-hand limits do not match. So all the values for which C of x is discontinuous, C of x is discontinuous at x equals 1, x equals 2, x equals 3, x equals 4, x equals 5. Or if you wanted to write that as a list, it's discontinuous at x equals 1, 2, 3, 4, 5. And actually it would keep on being discontinuous at integer values for x. So there's your idea of continuity. Just a quick review. Remember that there's 3 steps to test for continuity. 1 is for continuity at some number a is f of a defined. Does it exist? And if that's true, then you go do 2. Does the limit as x approaches a from the left equal to the limit as x approaches a from the right? Are those two equal? And if that's a yes, then question number 3 in short terms is, does 1 equal 2? If the answers to step 1 and step 2 match, then it's continuous everywhere. So you always go through those steps. Let me know if you have questions. Just post in this folder.